So welcome to Math 140, Calc 2. This is lecture 6. And what I want to do today is I want to talk a little bit about exponential functions and logarithms. I want to, as time permits, discuss some of the applications. There's a couple of different ways of defining the exponential function. One is through an infinite series. The other is through compound interest. I want to talk a little bit about both of them, talk a little bit about logarithm laws. So you watched a video on this, but this is such an important topic. I really want to emphasize because too often we get into the habit of we do things because we do them. And nobody ever stops to be told, why am I learning this? What is the purpose of learning this? Well, it's in the curriculum. I remember my first year at Williams, I was teaching Calc 1, and I was talking with the TAs about what do we want to cover in the class this year. And they're like, I can't really have my jaw drop to imitate. Well, I mean, I can, but it kind of loses the effectiveness in the math class. You get to choose what you cover? Yes, there's some choice. Every time you choose to cover something, it means you are not covering something else. It's the daily Java update. Excellent. And so what do we want to cover? Well, now that we have graphing calculators and programs online, we spend a lot less time in Calc 1 talking about how do you actually plot functions. It's a useful skill, but we spend less time on it. We spend almost no time discussing how to use a lookup table. I am old enough that I had to learn how to use lookup tables for logs and trigs and whatnot. I am not old enough to have had to learn how to use a slide rule, but I do have slide rules and I can bring them and show you what they're like. But how many people in their high school or junior high school class did the teachers explain why we care about logarithms? Or was it just, here's another function we can study? So you always want to ask, forgive the language, who gives a shit question? Why do we care about this? Why are we learning this? Right. So this is the slides we did. And again, I'm going to just do this really quickly. So you can see the sun. If not, your vision is really bad and get it checked. You should still be able to see the dot that's the Earth. There's an arrow pointing to it right in the center. And then there is the moon over there. And you might begin to wonder at that point, is that really the moon? Or is that just a piece of dirt on the screen? There's other pieces of dirt that are actually larger than the moon, potentially. At least on my computer screen. I haven't cleaned my computer screen in a while. And I can see differences between my screen and what's over there. One of the great powers of logarithms is it allows you to take things that span many orders of magnitude and put them all in one conversation. And another application is it takes relationships that are not linear and linearizes them. So I gave you a plot over here of the 100 most populous cities. And when we do a log-log transform, when we plot the log of the rank as the x-axis and the log of the number of people as the y-axis, it now becomes a linear relationship. We understand straight lines. This is one of the main themes of Calc 1. You give me a straight line, I'm happy. So if I have a function that converts things that are not straight lines to straight lines, wonderful. Study it when it's a straight line and then invert to get back to the original thing when you're done. So this is two real good reasons as to why we care about logarithms. So just very quickly, if x is b to the y, we call b the base, then log of x base b is y. This is the definition of the logarithm. It's how many powers of b do we need to get x. So what do we have to raise b by to get x? And you've seen numerous times how to calculate logarithms. We normally use base 2, base e, or base 10. In high school, what does log mean? What base? 10. In college, log means base e. We really don't use ln, the natural log. I actually don't like using ln. It could look like a 1 times an n, although you would never really write 1. We basically just use log in college for the base e because we never want to use base 10. When we're doing things theoretically, base 10 is not nice. It's base e that has the nice properties. It's the same reason why we use radians when we do trigonometry, because the derivative of sine is cosine only when you use radians. If you use degrees, you have a 180 over pi conversion factor. All right, so this is one of the most wonderful pictures I've ever seen in my life. We start off the radius of a proton, 10 to the negative 15 meters, and then we go all the way up to the radius of the visible universe. This is over 40 orders of magnitude. And just trying to grasp your head, going from something the size of a proton to the size of the visible universe. And we're putting this all on the same scale so we can try to make sense of things. And so you can say, well, I've only really moved 1 unit to go from here to here. Well, that's a factor of 10. And it just gives you a sense of just how much you're walking up. So it's really worth looking at something like this when you want to discuss physics at these incredibly large scales. If we were to try to plot a lot of these things simultaneously, we could not do it on a normal plot because the big things would just force the values of the function. We'd have to have the y-axis going so high, everything else would be clustered around 0, and we couldn't distinguish anything. But when we do logarithms, it allows us to spread things out a bit. All right, so there's a lot of different places where you see logarithms as units of measurements. We've seen them in the Richter scale to measure magnitudes of earthquake. So if you're 1 point higher on the Richter scale, it's actually 10 times worse. We've also seen it in decibels. And deci makes you think, okay, it's probably maybe going to be, maybe every time we go up by 10, that might be 1 order of magnitude. The pH scale in chemistry is another good example of a logarithmic scale. Okay, and so we typically like to do things in either base 2, base E, or base 10. If you're doing a lot of scientific papers, if you're not really doing calculus, you can make the argument maybe we'll use base 10 because people like to work in base 10. But if you're ever going to do calculus, you really want to do things in base E. And then just giving you a little bit of a plot of the different functions. The one on the left is plotting the exponential functions. And not surprisingly, if you're greater than 1, well, actually just even greater than 0, the higher the base, the faster you grow. Well, that makes sense. Your 2 to the x is growing faster than 1.5 to the x, and it's growing slower than 4 to the x. When you are negative, it goes the other way because then it's going to flip things around. A similar thing is true for the logarithm, except now it's the opposite. So for the logarithm, the smaller the base, the faster it's growing for inputs greater than 1. And if you think about it, if I give you a number, 1024, 1024 is 2 to the 10. So the log of 1024 base 2 would be 10. What would the log of 1024 be base 10, approximately? So approximately, what would the log of 1024 be base 10? 3. And so you can see I need a lot more powers of 2 to get 1024 than I need powers of 10. Well, that makes sense. 3 powers of 2 is not even 1 full power of 10. And so that's why you can see that the logarithm base 2 is going to be above the logarithm base 10 when you're greater than 1, and then it's going to flip when you're less than 1. So you always want to have a sense of what the functions look like. And these are inverse functions. The exponential, the natural log of x is x. I raise e by the number of powers of e I need to get x, I get x. Or I take the natural log of e to the x, and that's just going to be x. And so we discussed many orders of magnitude. We discussed how it linearizes functions. And you're plotting things over here. I'm plotting on the left x to the 0.25, x to the 0.5, x squared, and x to the 4. And I'm just plotting it from 0 to 10. So I mean, I'm not doing anything completely absurd. I'm not going up to 10 to the 5th, or even 10 to the 10. I'm just plotting up to 10. And when you look on this scale, which functions can you see on the left? You can see the x to the 4 clearly. You can see the x squared. And you can see that the x squared is different from 0. Barely. By the very end, it is a little bit above 10. Can you see the x to the 0.5 and the x to the 0.25? No, they seem to be indistinguishable from the x-axis. And if I just plot the highest two, and I'm only plotting up now to, I'm sorry, I'm plotting the next x to the 0.5 and x squared. And even for there up to 10, I can barely see the x to the 0.5 growing. I can see it, but it's hard. You can do the same thing with logarithms. And now what I do on the right is I'm doing a log-log plot. And we'll see this later in the semester when we do the method of least squares or linear regression. When we take some data and we try to discover how is y related to x. Well, if it's linearly related, it turns out we can write down in closed form an expression for what the answer is going to be. And now all of those different functions become straight lines. And now the 0.25, 0.5 squared and 4th powers, they just become lines of different slope. And so when I do a log-log plot, the x to the 4th is going to be a straight line with slope 4, the x to the 0.25 is going to be a straight line with slope of 0.25. I can see them now all in one plot. All right, so one of the big themes in mathematics is once you know something, hammer away, keep using it, don't throw it away. What else can you get from it? So all the rules for integration come from rules for differentiation. And the rules for differentiation come from rules on limits. So the log laws come from the exponent laws. So I have found over the years, people often have trouble with the exponent laws. So at least when everything is an integer, these should be familiar. If I take b and I raise it to the mth power and I multiply it by b to the nth power, it's b to the m plus n. And you can think of this as, for example, if I have b squared b cubed, this is b times b times b times b times b. Okay, now I just count how many b's do I have? 1, 2, 3, 4, 5. It's b to the fifth. This is not a proof. This is just motivation. This is just example. This is just trying to give you a sense of, is it true? If you remember that there's some kind of relation, and I can't remember, is b to the m, b to the n, is it b to the m plus n, or is it b to the m times n? Let me just try a specific case and see what's going on in that case. As long as I know there's roughly some formula, would be a really bad choice. Instead of doing b squared times b cubed, would be a terrible choice to do. If I'm trying to figure out, is it m plus n or m times n? I'm sorry? Well, that would just be more work for me, but it wouldn't necessarily be bad. There's a bad choice. Yeah, if I did 2 and 2, right? If I did b squared times b squared, it's b to the fourth. But is that b to the fourth, b to the 2 plus 2, or b to the 2 times 2? So you sometimes have to be a little bit careful. You get points for doing an example, but you then lose some points for not doing a good enough example to actually distinguish the two cases. For the next one, b to the m over b to the m, let's say I had, b cubed divided by b squared. This would be b times b times b over b times b. Well, you see we can cancel 2 of the b's. Okay, and that provides some justification. And then similarly for the last one, b to the m to the n, I could do, b squared cubed is b times b times b times b times b times b is b to the 6th. So again, these are not proofs, but these are at least, motivations. And again, this is the same stuff that's, gone below. Very similar examples, using 3's and 2's, good numbers, good small numbers. Okay. The 4 really important log laws is the log of x to the n is n times the log of x. The log of a product is the sum of the logs. The log of a quotient is the difference of the logs. And the last is the change of base formula. The log of x base b is the log of x base c divided by the log of b base c. And again, I will post all of these notes after class today. These notes also have the proofs of all of these. I encourage you to look at the proofs. It's nice to know where things come from. If you really want to challenge, try to prove them first. And then you'll see what you're able to. It really comes down to just working with the definition. There is sometimes another log law that's isolated. Sometimes you do the log base b of x inverse is negative log base b of x. But I claim we don't really need that. But it's sometimes nice to just isolate. Why don't we necessarily need that? Yeah. It's the same thing as the first one. But what if I say, I don't want you to say it's the same thing as the first one, because for the first one, I want n to be a positive integer. So I won't let you say it's the same as the first one. Is it the same as any of the other ones? So you can't use the first one. Is it the same as something else? It's the same as the quotient. So what would you choose for x1 and what would you choose for x2? Yeah, so x1 would be 1 and x2 would be x. So if we know the quotient rule, we actually get this for free. So you have to sometimes be careful. how do we prove the first one? Are we proving the first one when n is just any integer? Is n a positive integer? Can n be any real number? What are the conditions for it? If we only proved it for positive integers, we can't use it to immediately get the log base b of x inverse. Now, we can actually prove it for n as a real number, so it's not a big deal. But it's just something to be aware of. We can get it from the quotient. And so sometimes when you're proving calculus results for derivatives, you might just prove the quotient rule and not prove the formula for what's the derivative of 1 over f, because you get the derivative for 1 over f basically for free from the quotient rule. Okay, so and then it's just you're proving the log laws. So what I'm going to do is I'm going to just put the slides up for a second so that if you're ever watching the video, you can just pause the video over here. Here is the proof of the power rule. We'll just do this one, we'll not do the other ones. So very similar to the definitions of the derivatives, giving us the proofs of derivative laws, it's the same thing here. The derivatives, the definitions of the logarithms are the start of all the proofs of the log laws. So I want to prove the log base b of x to the n is n times the log of x base b. The log of a power is that power times the log. And so I start off with, well, what does the log of x base b equals y means? It means x equals b to the y. Well, I want to take the log of x to the n, so why not raise both sides by the nth power? And so I get the log, so I get x to the n is b to the y raised to the n. And now I use my exponent law. That if I have b to the y to the n, that's the same as b to the y times n. And this is what I mean that the log laws come from the exponent laws. Well, n times y times n, I can write it either way. Multiplication is commutative. So now if I take logarithms, oops, this is a typo. This should be. Does anybody know what a kludge is? So a kludge is something that works, doesn't have to be elegant. I just took a snapshot of a white box and just put it over that. And now I can just draw the exponent in a bit like that and fix it. Okay, I'm not going to prove the next one. The log of a product is the sum of the logs. But again, it just go through the definition. Proof is very similar. Log of a quotient is the difference of the logs. You could also do it another way. You could prove the log of 1 over x is negative log x, and then use that to get the quotient rule from the product rule. So if you prove the quotient rule, you can get the reciprocal rule, or if you have the reciprocal rule and the product rule, you can get the quotient rule. And the last one is the, sorry, did I get rid of it? Oh no, here it is, okay. This is the change of base rule, okay. All right. And then I'm not gonna go through the stuff over here. This is just more plots on how things go. All right. Any questions on logarithms, exponentials at a high level? So hopefully we've now motivated why we care about these functions. There's a reason why we introduce these functions. The question is always now, how do we compute them? So there's two definitions for e to the x. One definition is e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... And this is the sum, and it goes from 0 to infinity of x to the n over n factorial. N factorial is n minus 1, 3 times 2 times 1, with 0 factorial equals 1. And you can view the factorial function as it's the number of ways to order n objects when order matters. So president, vice president, secretary, treasurer, we have 4 positions, we have 4 people. There's 4 factorial, 4 times 3 times 2 times 1, or 24 ways to assign the 4 people to the jobs. What if we have no people? How many ways can you order no one? There's one way to do nothing. So we define 0 factorial to be 1. It's a useful definition. It makes a lot of the formulas nice. As an aside, does anybody remember what n choose k is? The binomial coefficient. If you don't remember the formula, do you remember what the interpretations of n choose k? So this is the number of ways to choose k people from n when order does not matter. And it's n factorial over k factorial n minus k factorial. Yes. So for instance, if I take everybody in this class and I want to choose 3 people, it doesn't matter which order I choose the figure. I could do me, you, and you, which would be the same as doing you, me, and you. All that matters is which 3 people are chosen, not who's chosen first, who's chosen second, who's chosen third. Think of this as the House of Representatives or college council, and everybody is an equal voter. We don't have opposite positions. We don't have people different. I just care who's chosen, not are you chosen first, second, or third. If you think about it, if I have 10 people and I want to choose 3, how many ways are there to choose 3 people from 10 when order matters? It's 10 times 9 times 8. 10 for the first, 9 for the second, 8 for the third. But what if I didn't care about order? Well, how many ways can I reorder 3 people? There's 3 factorial or 6 ways to reorder. Once I have my 3 people, I have 3 choices of who's first, 2 choices then of who's second, and 1 choice on who's third. So if I want to remove ordering, I look at how many ways can I choose people when order matters, and then I divide by k factorial. And that's where this k factorial down below comes from. The n factorial of n minus k, that is giving you how many ways can you choose k people when order matters. And then we divide by k factorial, and that's going to be how many ways there are when order doesn't matter. So for example, what would 5 choose 2 equal? How many ways can we choose 2 people from 5 when order doesn't matter? Well, according to this, it would be 5 factorial over 2 factorial, 3 factorial. This is 5 times 4 times 3 factorial over 2 factorial, 3 factorial. You can see that I wrote it like this because the 3 factorials will cancel. And this will be 5 times 4 over 2 times 1, which is 10. And if you think about it, how many ways can I choose 2 people? From 5 times 4 is 20. But I have 2 ways of ordering them, the first person and the second person. So there's really 10 ways to choose. So this makes sense. How about this? How many ways are there to choose 2 people? I'm sorry, to choose 5 people from 2? What do you think the answer should be? None. So the answer should be 0, right? Let's think, what would 2 factorial over this be? It'd be 2 factorial over 5 factorial, 2 minus 5 factorial. So this is 2 factorial over 5 factorial, negative 3 factorial. So negative 3 factorial is what? What's the only way that this could be 0? What should negative 3 factorial equal? We want this to be 0. What should negative 3 factorial be if we want this to be 0? I'm sorry? Well, if we had negative 3 factorial being 0, we would have 2 divided by 120 times 0, 2 divided by 0. What's 2 divided by 0? That goes off to infinity. So you went the wrong way when you made it equal to 0. What do we want negative 3 factorial to be? We want it to be infinity. So it turns out you can extend the factorial symbol, and when you extend it, negative 3 factorial, in fact, any negative integer factorial will be infinity. Yes?
So what is factorial exactly mean?
For negative numbers?
Like for like positive or negative?
Well, for positive integers, there's a combinatorial interpretation. For negative integers, there's no combinatorial interpretation. It's a generalization of the function. And it has a nice interpretation when the input is a positive integer or 0, but you no longer have that interpretation for something like negative 3. But there's a way to define it. There's actually a way to generalize the factorial to any number, My favorite is -1/2 factorial is the square root of pi. And this is extremely important in statistics. This is stuff we don't need to know. The whole point I want to mention here is that we started today by talking about the exponential and the logarithms. Why are we defining these functions? What are they useful for? Where are they defined? The exponential function takes any real input, but its output is a positive number. Logarithms can only take positive numbers as input, but their output can be any real number. You always want to ask, where is a function defined? We start off with the factorial function. We have to decide, what do we want 0 factorial to be? It turns out to be convenient to have 0 factorial equal 1. What do we want the negative factorial to be? It turns out it's natural to make this equal to something like infinity. So we had one definition of e to the x. Here's another definition. E to the x is the limit as n goes to infinity of 1 plus x over n to the nth power. And this is the compound interest. And so you should hopefully remember the formula. Let's say you start with P naught money. Rate is R% per year. I want to say R%. So if it's 100% per year, what would R equal? 1. Okay. So 100% per year is R equals 1. Say you compound n times a year. So you start off with P naught. After one period, you have P naught and you have 1 plus, you split the interest rate into n equal amounts. And this is how much money you would have 1 unit later. It's the amount you started with P naught plus the effective interest rate R over n times the amount you have. And what's great about compound interest is the money you make starts to make you money as well. And so after 2 periods, how much would we have? It'd be 1 plus R over n squared. Because every time we move forward a period, we multiply by 1 plus R over n. And we keep doing this. And after 1 year, it's 1 plus R over n to the n. So we grow by a factor of 1 plus R over n to the n in 1 year. And so the question becomes, which do we want to do? Do we want to have the interest compounded more often or less often? What do you think? Would you rather have the interest all accumulated once at the end of the year? Or would you rather have it more times? Which is better for you? So it might effectively flatten out. At some point, you're doing it once a day versus once an hour versus once a minute versus once a second. At some point, we no longer really see it. Let's look at once a year versus twice a year. So once a year, let's assume that the initial money is just $1 to be easy. You should go from $1 to 1 plus R in 1 year. If you do twice a year, and again, your P naught equals 1, you go from 1 to 1 plus R to 1 plus R, I'm sorry, 1 plus R over 2 to 1 plus R over 2 squared, which is 1 plus 2 times R halves plus R squared over 4 is 1 plus R squared over 4. That's a little bit better. If we do it 3 times a year, what does twice become if you do it 3 times a year? Fancy way of saying that? Thrice a year I have no idea what 4 times 0 becomes. So 1 would go to 1 plus r thirds cubed. And now we use the binomial theorem. It's going to be 1 times 3 times 1. So this is actually 1 cubed. 1 squared times r over 3 plus 3 times 1 times r over 3 squared plus 1 times r over 3 cubed. So this is 1. The 3's cancel and we get r. Now we have r squared over 9 times 3. So it's going to be r squared over 3, right? Plus r cubed over 27. Is that better than what we had before? Is that better than twice a year? Why is it better than twice a year? Is it better than twice a year for any positive r? So which would you rather have, r squared over 4 or r squared over 3 plus r cubed over 27? Which is better for you? I'm sorry? I can't hear you. So why is r squared over 3 plus r cubed over 27? Why is that greater than r squared over 4? So we need to compare this to this, right? Which would you rather have, r squared divided by 4 or r squared divided by 3? Which is going to be more for you?
Wait, is the bottom one r cubed or r squared?
It goes 1 plus r squared over 3 plus r cubed over 27. And the top is just r squared over 4. They both start off with 1 plus r.
So the bottom one,
So why is the bottom one better?
because they're both r squared, but you're dividing by them.
Yeah, so if you're dividing by 3, that's not going to decrease it by as much as dividing by 4. Now, in a remarkable show of ignorance, there was a fast food chain, it might have been Wendy's, I'm not 100% sure, that introduced the 1/3 pounder or something like that. So you've heard the story. And a lot of people said, well, why would we buy the 1/3 pounder from you when we could get the 1/4 pounder from McDonald's for the same amount? And it actually lost money for the company because people thought it would be better to have a 1/4 pounder because 4 is bigger than 3. Yes, 4 is bigger than 3, but it's in the denominator. So it actually hurts you to have the bigger number. So this actually has shown that just going from once a year to twice a year to thrice a year, the more times we do it, the better. You then want to keep showing that as you keep doing it more and more times, it gets better and better and better. And then the question becomes, what happens if we take the limit as n goes to infinity of 1 plus r over n to the n? What does that equal? We can try to figure out what does this look like. And so if we have 1 plus r over n to the n, it's going to be 1 plus n choose 1 r over n to the first power plus n choose 2 r over n squared plus n choose 3 r over n cubed plus dot 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 n choose n r over n to the n. Okay, now r is going to be less than 1 typically, so r over n raised to the nth power. The further we go, the less that's going to be because we're dividing by n is getting huge. Let's just start to see what this is. N choose 1 is just n times r over n, okay? Then we have n times n minus 1 over 2 factorial r squared over n squared plus n minus 1, n minus 2 over 3 factorial r cubed over n cubed plus dot dot dot. And now what I'm going to do is I'm going to say, this is calc 2. I don't have to prove things rigorously. I just want to do enough to give you a sense of what's going on. So it's going to start off as 1. What is n times r over n? It's just r. Now for the next one, n times n minus 1 over n squared. What is n times n minus 1 over n squared approximately if n is huge? N times n minus 1 over n squared is approximately what? So think of n as really, really big. N times n minus 1 over n squared. We can cancel one of the n's. So it's just n minus 1 divided by n. What is n minus 1 over n when n is huge? 1. So that, as n gets really, really large, the next term looks like r squared over 2 factorial. For the next term, we have n minus 1 over n minus 2 times n minus 2 over n cubed. N over n is about 1. N minus 1 over n is about 1. What's n minus 2 over n? It's about 1. You think of n as a quadrillion. So the next term is approximately r cubed over 3 factorial. Does that look familiar to you? Looks like 1 plus r squared over 2 factorial plus r cubed over 3 factorial, or the sum, n goes from, I'll do m goes from 0 to infinity, r to the m over m factorial, which is e to the r. So this is a rough argument that the two different methods actually give the same answer. Okay. Sometimes one formula is better than another. We have two different ways of talking about this number e. We have the series expansion that we're defining e to the r to be the following. And then we have this compound interest. And again, what I'm doing today is I'm just trying to give you a sense of where things come from so that when you're manipulating things, you have a sense. Now, if I give you e to the x times e to the y, what should this equal? It should equal e to the x plus y. But what's really going on is e to the x is the sum, and it goes from 0 to infinity of x to the n over n factorial. E to the y is the sum, say m goes from 0 to infinity of y to the m over m factorial. And this is the sum, say k goes from 0 to infinity of x plus y to the k over k factorial. So if I give you 10 to the x times 10 to the y, we know what that is, at least if x and y are integers. We're now defining these powers with the strange number e, and we're not forcing x and y to be integers. So what do we mean when we say e to the x? We technically mean this infinite sum. What's nice about this infinite sum is it makes sense for any value of x. I know how to square things, to cube things, to fourth power things. I can do x times x times x times x, not a problem. What does it mean to take the square root of 2 to the power of something? I don't know. That's much harder. So we now have to prove that this is true. And so again, I'm going to just do a high level sketch. So high level sketch. I can write this as the sum, k goes from 0 to infinity, the sum L goes from 0 to k of x to the L, y to the k minus L over L factorial k minus L factorial. You have to justify that you can rearrange terms. We can't always rearrange terms. What I'm doing is I'm collecting all products of x and y such that the sum of the powers is k. So I'm splitting it up so that I collect all things that have the same powers. So when I multiply everything out, I've got 1 plus x squared over 2 factorial plus dot dot dot. 1 plus y squared over 2 factorial plus dot dot dot. When I multiply it out, I get 1 times 1 is 1, plus x plus y. Those are all my linear terms. Then I have my quadratic terms. I have x squared over 2 times 1, plus x times y, plus y squared over 2 factorial. Then I would have the cubic terms. I would have x cubed over 3 factorial. And then I would have an x squared times y over 2 factorial 1 factorial. And I would have an x y squared over 1 factorial 2 factorial. And then I would have a y cubed over 3 factorial. And then I would have the fourth power terms. And so I'm just collecting things. Okay? So much of mathematics is all about pattern recognition. And that's one of the reasons why I want to just briefly show this. We have an L factorial and a K minus L factorial. Does that look like part of anything we've seen before? Where have we seen a denominator that looks like L factorial K minus L factorial? We saw that somewhere earlier today. In the combinations, what did we want for the numerator? So if that's the denominator, what should the numerator be? K, not quite close to K, yes, K factorial. Now, if you try to be excited, say it's K factorial with an exclamation point for emphasis, that's actually the double factorial. You have to be careful because the double factorial is not what you want. Am I allowed to just multiply the numerator by K factorial? Can I do that? I can't just multiply the numerator by K factorial. So what do I have to do? If I multiply the numerator by K factorial, what do? I can multiply the denominator by 1 over K factorial. And now when I do this, what I notice is this part over here is very nice. And this part over here, it doesn't depend on L, so I can move that out. And then this is just going to become the sum. K goes from 0 to infinity, 1 over K factorial, and I'll have the sum, L goes from 0 to K of K choose L, X to the L, Y to the K minus L. But this part over here, we've seen this before. Anybody remember what that is? It's the binomial theorem. You're foreshadowing. We saw Pascal earlier in the semester. So using that's the binomial theorem, this is then just the sum, K goes from 0 to infinity, of X plus Y to the K over K factorial, which is what we wanted to show. So we've actually shown that e to the X times e to the Y really is e to the X plus Y. The notation is good. It's not bad notation. But it's technically 2 infinite sums equals a third infinite sum. And then we have to justify that, yes, everything does reduce nicely. And so we now have the exponential function that we can work with. So I want to just recall from calculus. Recall from calculus. What is the derivative of e to the X? E to the X. Did they ever prove this for you in your calculus class? So here's a sketch of the proof. The derivative of e to the X is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot, dot, dot. What is the derivative of an infinite sum? Yeah, why not? The infinite sum of the derivatives. Let's just say we can interchange the sum and the derivative. You have to justify that. Moving on, you can do that in a higher level math class. You can justify it. Let's take the derivative term by term. What's the derivative of 1? 0. What's the derivative of x? What's the derivative of x squared over 2 factorial? 2 times x over 2 factorial, which I can write as 2 times 1 factorial. What's the derivative of x cubed over 3 factorial? 3 times x squared over 3 times 2 factorial. Next one would be 4 times x cubed over 4 times 3 factorial. So this is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial is e to the x. So here's a way to justify the derivative of e to the x is actually e to the x. If we can differentiate this infinite sum, then the derivative of e to the x is e to the x. So again, I'm trying to review some of the stuff you've done in Calc 1. I know it's been a while for some of you. So if we now have the derivative of e to the x, what's the other function we want to have the derivative of? What's the complementary function to the exponential? The log. So what is the derivative of the log of x, which is the natural log of x? What's its derivative? 1 over x. And here is a really valuable result. So theorem. If f of g of x equals x, then g prime of x is 1 over f prime of g of x. And the proof is, by the chain rule, we get f prime at g of x times g prime of x equals 1. So solve for g prime of x. That's not a factorial, that's just example. Okay? So by the chain rule, if I have two functions that compose and give me the identity function that just take x to x, then f prime of g of x times g prime of x equals 1, so I can solve for g prime of x. All right, so now let's use it. Let's take the exponential of the natural log of x. That equals x. So here, f of x is e to the x, g of x is the natural log of x, f prime of x, oh, we just showed that's e to the x, f prime evaluated at g of x is e to the natural log of x. What is e to the natural log of x? We raise e by the number of powers of e we need to get x. It's just try to be consistent and write log. So this is just x. So the derivative of the natural log of x is 1 over f prime at g of x is 1 over x. So when you did Calc 1, did they tell you where the derivative of natural log of x comes from? Did they tell you why it's 1 over x? So it's good to just get a sense of where these things are coming from. There's other ways to get these derivatives. You could actually start off with the natural log, find the derivative of the natural log, and then use that to get the derivative of the exponential. Now you can go in the other direction. I like to start off with the derivative of the exponential. All right, so we actually finished the entire unit. It just turned 9:50. Question? Okay, so this is a good place to stop. Have a good rest of the day.